For the sake of time, it's 8:37, so we're going to go ahead and get started. And certainly we are grateful for those of you who are able to be with us now, and also those who are considering watching this later on. And so this will be recorded and we will post it and make it available. I'm grateful in particular because it's not often the case that anybody wants to show up on a Friday morning to talk about math. And we, in our somewhat more constrained world, are often very excited to talk about these things, even on a Friday morning. And so we're, again, grateful for the chance to be able to step back and to consider what it is that we are doing with math at ACA. And in particular, the hope for this morning is that we're going to paint a picture of where we want to end up with math. And so as with anything we do at ACA, we want to start with the end in mind and ask ourselves the question of what does it really look like for a graduate of ACA? And what education will he or she have received, in particular this morning, in the realm of mathematics. And so we're going to spend the bulk of time talking even about the upper grades. The way that this will look is I'm going to talk a little bit about what we're doing in the lower school. I'll pass things off to Mr. Andrew, and then he will connect him to Mr. Clausen, and to paint a picture of really what we're doing, again, in math overall. And one of the things that I want to admit on the front end is that a lot of times math is a subject that we can take for granted. I haven't heard anyone make a compelling or even a serious argument to say, you know, what we shouldn't be teaching at school is math. Just not there. And so it's taken for granted. Like, we should be teaching math, and yet we don't often ask the question of exactly why we should be teaching math. So it's an important question for us to step back and to not just say, well, we teach math because we should. Certainly there are practical elements of math that we would value, and as it's taught in kindergarten, as it's taught in 7th grade or 12th grade, and there are practical skills vocationally that will be helpful. All of that is true, and yet at the same time we're aiming for something that is broader in our aims for math overall. And a part of those broader aims connects to even the curriculum that we choose to use in the lower school, and how that connects to the upper grades as well. And that we use a curriculum that is in the category of what's called Singapore math. Singapore math was developed in the 80s, as you might imagine, in Singapore. And one of the distinctives to it is that it often would stand out from the way that many of us learned math, and that you have this dance of sorts that goes between concrete, pictorial, and abstract, which might sound like just terms that are broader, but rather it's one of the things that's important for it is we're not just talking about procedures. And so you might notice, for instance, in your child's math books, if you're a lower school parent, that we're not just thinking about how do you compute these numbers, but what's going on with them. Do we understand the concepts that are behind the computational side of what we're doing? And so especially in kindergarten, 1st and 2nd grades, we spend a lot of time working on fundamentals. And so it might seem at times like the pace is slow there, and yet that's by design, in the sense that we want students to become really comfortable not only with understanding the concepts behind math, but growing in even some of their practical skills behind it. And so you might also hear some of your child's teachers talk about math facts, which we're emphasizing more heavily this year, and that we want our students to be more and more comfortable even being able to compute in their minds. And so this balance between having students understand math and the concepts behind math, and also being able to compute, is something that's really significant, especially for students later on in endeavors within mathematics. One of the more abstract things that we would affirm also is the reality that we want students to grow in their mental habits. The way they think is often shaped by subjects like math. And that's not just the case, say, as you get later on into geometry and as they're doing proofs and working through logic, but that's the case really early on. And we want to help students work with manipulatives you might have seen if you're a lower school parent, where they've got practical physical objects that they're working with, or even things like bar modeling, which is an approach that you might have seen your student use as well, where they're beginning to see physical representations of the concepts or even word problems that they're seeing from a very early age. And so those are some of the reasons that we dove into Singapore math, and that's really fundamental to where we are, is that idea that we're not just working on procedures and putting numbers together, but we're also giving visual representations to math and giving students tools to be able to dive into problems in different ways. This really connects even in many ways to our approach to literacy, in that we want students to have the tools to engage with ideas. We want for them to be able to recognize, you know what, there are multiple ways even to solve math problems. It's not just that there's one approach. and that pattern of thought, and even the perseverance to connect it to our virtues that's required for that is really significant for where we are as a school. That said, that's a little bit just about where we are in the lower school math side of things. And I will pass things off to Mr. Andrew, and we will go from there. Mr. Andrew.
Great. Thanks, Mr. Knowles. Well, welcome. It's always a joy to talk about math with our families here at Atlanta Classical. It unfortunately is a subject that sometimes is overlooked because it seems that the nature of a classical school is to fixate on the humanities. And yet when I look at what our graduates have done, so many of them have gone on to study engineering, have gone on to study neuroscience, chemical engineering, math itself. And so it's apparent that many of our students have interests in these STEM fields, and they got that interest somewhere. So I think it's really important for us to be examining our work as teachers here at Atlanta Classical and thinking about our math program in particular. And that's what we'll be doing today with you all. When I first joined the school in 2016, I remember that teachers and administrators returned to one image to talk about instruction. And that was the idea of this iron triangle, they said. And the principle that sort of undergirded all of instruction at Atlanta Classical was this iron triangle, which was made up of, as you can imagine, 3 points. Those 3 points are students at one point, teachers, and books. So the notion is that when you strip away all of the school's gadgets, its extracurricular activities, its programs, its technology, what you're left with are those 3 things. You are left with students, the ones who learn. You are left with teachers, the ones who model and facilitate and lead that learning. And then you are left with the books themselves, right? The texts that give life to learning. And when Mr. Knowles and I, a couple of years ago, began to reevaluate the quality of our math program and think about how we could continue to kind of raise the level of excellence, those 3 points informed our questions, right? They informed our considerations about what it would look like to continue to move our math program forward. And so the questions were, do we have the right students in the right math classes? Do we have the right teachers in front of our students? And then finally, do we have the right books? Now, the question of right students and right classes is not a matter of getting rid of students, right? It is instead an acknowledgement of the fact that math is cyclical, math is cumulative. So that is to say, it grows on itself, it builds on itself. And so it's absolutely essential for a student's success in mathematics that he or she is placed in the proper class, especially in the transition from elementary school to middle school and high school, as you move from simple arithmetic to abstract manipulation that happens in algebra. If a student doesn't have the essential skills, the kind of baseline knowledge to be able to encounter more abstract concepts in mathematics, we've seen that they can really begin to flounder in the middle school years and then struggle mightily through high school. And so one of the efforts that we began last year was to put a lot more thinking into the placement process, especially as a student, again, moves from 6th to 7th grade. And so we introduced the MAP test, the measure of academic progress, as a way of evaluating the skills that a 6th grader might have so that we can place them appropriately in 7th grade, which places them on a track that culminates in the 12th grade. Now, that is not to say that we pigeonhole a student and leave them in a track to languish for the rest of their academic career, right? We're a small school, which is to say we know our students and we see their strengths and we see their weaknesses. And if a child is farther ahead than they ought to be, there's opportunities to hold them back. If a child is thriving and needs to be challenged, there are opportunities to move them forward. So these placements are not permanent. They don't restrict a student's capacities to flourish, right? They are instead intended to position our students for success. So again, this is one effort that we've made in the upper school to kind of perfect our process, to give a lot more attention to placement and then to reevaluate that throughout a child's progression through the grades in the upper school. The second question that we then ask is, do we have the right teachers in front of our students? Since the very conception of our school, the kind of defining principle for hiring faculty was looking for folks that were subject matter experts, right? That were masters of their own discipline. However, the thing that we know about the best teachers is that they don't just know their discipline well, but but they can do the second thing of making that knowledge accessible to students. It is one thing to be a genius in a subject, but it is quite another to take that knowledge and deconstruct it and make it available. That is its own kind of genius. And it is one that requires patience and kindness and humility. And so as we've made hiring choices over the last 2 years, we have prioritized looking for those kinds of people. And as I think about the math hires in particular that we've made just last year with Mr. Clausen, Mr. Thiel, and Mrs. Wilson, who's in our Algebra 2 classes. We also have Mr. Dawson on this call, who has taught math in the past, but is one of our science teachers. The thing that we've prioritized again is both the folks that know the subject, but then have thought hard about what it looks like to make that knowledge accessible to a child, which again is a tremendous achievement when it happens. The final thing that we asked a question about was the books that we were using. Now, any good math teacher will tell you that a book is only a starting place. Whereas in English class, students and teachers will kind of live within the world of a text. In a math class, the book is kind of an ordering principle for the class. It provides a sequence of learning that would help a student kind of pick up where they left off in the prior year and then continue into the next one. And so in many cases, the book offers a foundation, but it is not the end of a student's learning in a given math class. 2 years ago, we again kind of launched an effort to reconsider what curriculum we wanted our students to be using in the middle school through Algebra 2. And we landed on a series of textbooks by Pearson called Envision. And we chose it for 2 reasons. One was to make sure that we had a kind of logical sequence that students would follow all the way from the point at which they left the elementary school to when they began to enter pre-calculus and calculus. And the second was that Pearson does what Mr. Knowles described, or they offer what Mr. Knowles describes the Singapore math program doing, which is to say occasion for students to move between concrete, pictorial, and the abstract, right? For students to both master skills and then to think conceptually about math. So again, as we've thought about instruction at ACA, we've really been thinking along the lines of what are our students, or do we have the right students in the right classes? Do we have the right teachers in front of our students? And finally, are they using the right books? Now, the thing that I have not mentioned and the thing that I will defer to Mr. Clausen to talk about is what it means to do all of this classically. This in many ways is kind of the holy grail of math instruction. We talk a lot about just kind of doing the basics well, right? Making sure that our students are equipped to thrive in whatever discipline they might choose for themselves in college, whatever career they might choose. But this question about what it means to do it classically is something that is incredibly challenging, and one that we want to take seriously and begin to explore in our work at Atlanta Classical. So Mr. Clausen is going to devote, I think, his energy and time describing today what it means to teach math classically. And I'm happy to give him the floor and to not attempt to do this myself. So Mr. Clausen, from here, I'll hand things over to you.
Well, thank you, Mr. Andrew. Thank you so much to all of you too for listening in, whether that's right now or people on the recording. I appreciate it. I always love to talk math. And so when people listen, that makes it even better for me to talk about math. So I actually want to get started before tackling the big question of where does math fit in the liberal arts and in a classical education, going into a little bit more detail with our tracks, because like Mr. Andrew said, that's really important that we have students in the right classes. So at the end of 6th grade, we have every student taking the math tests. And from there, they're pretty much split into 2 tracks, into a regular 7th grade and an accelerated 7th grade. And those students, we'll say the regular is track 1. Those are students that need a little bit more time going through arithmetic. Those are students who need to think a little bit more in the concrete before they're ready to move into the abstract, into things like formulas, into things like variables. So those students are going to take 7th grade math, and then they're going to take an 8th grade math that sort of acts as a pre-algebra. And then those students in that first track are going to get tested again at the end of 8th grade to determine where they're ready to go in the high school. Students that score well will be placed right into Algebra 1, and that will take them through Algebra 1, Geometry, Algebra 2, and Pre-Calculus. And that's how they'll typically finish their high school careers. Students who still need a little bit more time before heading into the abstract world of algebra are going to take a fundamentals of algebra course and then take Algebra 1, Geometry, and then their choice and our choice of an Algebra 2 or an advanced mathematical decision making, AMDM we call it. And this is, you can think of it almost as like a life skills math class. Where are ways that you can see math sort of in the everyday life? How can you see the beauty in it? How can you see the order in it without going kind of further down the road in math? So those are our students who tested into regular 7th grade math. We also have a group of students that will test into an advanced 7th grade math. And those students will move on, and in 8th grade, they're ready to tackle algebra. They're ready for the variables. They're ready for the algorithms. And so they're going to take algebra in 8th grade, take geometry, Algebra 2, pre-calculus, and then in their senior year, they're going to be ready for calculus. And depending on how well they do in their pre-calculus class, depending on their ambition, depending on some teacher recommendations, they'll be either placed into a regular calculus class that will cover most of the basics of a first semester calculus class in college, or they'll be placed into AP Calc BC, which is an AP class that allows you to take a test that if you do well enough, you could pass out of up to 2 semesters of college calculus. So it will cover Calculus 1 and Calculus 2. It's a difficult class. It is for our students who are ready and raring to go and love math and want to really sink their teeth into it. So those are our 2 tracks, each of which sort of split into 2 groups of their own. And again, why do we do this? Like Mr. Andrew said, it's not to pigeonhole students. And it's rather to give students that firm foundation. Math builds upon itself so much that if you're rushed into things in math, it becomes so easy to be overwhelmed. It becomes so easy to be lost that we believe it's so much more beneficial to get that firm foundation. Take an extra year in the junior high, take 2 extra years before you're ready to enter that world of algebra. Because if you're still struggling to know off the top of your head how to do 7 times 13, it's going to be really difficult to do 7x times 13x, because that's a whole nother layer in there. And it also gives us a way to appropriately pace things. It allows students who might get ideas really well, but takes them more time to get those ideas. It gives them the opportunity to be given that time, especially in the junior high, when these ideas are really forming. So why don't we allow anything past Calculus 2? And why don't we allow students to take AP Calc in their freshman years so that they can go get their math degree before they're even done with high school? Well, because it's unnecessary, and in 99.999% of the time it's really harmful, actually. So I come from a school that allowed me to excel in math a lot. I finished calculus when I was a sophomore in high school, and it proved to be a challenge those next few years that I had to go off to college and learn how to take those college classes. And while I made it through, because I love math that much that I was determined to do it, I can tell you from experience, it meant some blood, sweat, and tears to try to get through it. And at the end of the day, I look back and see that meant that I gained 3 extra college classes that I couldn't have had otherwise. That's not even a full semester of classes. For 2 years of all of that effort, it earned me almost a semester of extra math, and that's it. And so rather than having our students get that stress, we would rather, again, see the firm foundations the appropriate pacing for a high schooler, and they will be ready to thrive. A student going into college ready to take Calculus 3 is well ahead of the game. So again, if you have any questions, I think Mr. Knowles sent it out to everyone in the chat. But if you have questions about anything, please do send them in, and we're happy to answer those questions at the end. But now for the exciting part, after the nuts and bolts, and that is, what is math doing in a classical school? Are we supposed to teach it like STEM? Are we supposed to just crack open old Greek texts about math and learn how to do math using Greek numbers instead of using our number system? Are we just counting in Roman numerals? Does that make it classical? What is it that we're doing? So I want to read from you the note that I actually sent all of my parents at the beginning of this school year. This is sort of my apology for math and the liberal arts. Like all true liberal arts, an education in mathematics aims for the cultivation of intellectual and moral virtue. This aim does not negate or ignore the very practical applications of math, but it does reach for a higher and more humane goal. Through the processes of memorization, repetition, and deduction, the student habituates himself to the moral virtues of perseverance and steadfastness. Hard work produces discipline, and discipline produces good character. Likewise, there is perhaps no other study that disciplines the mind as well as mathematics. In fact, as I'm sure Dr. Roth could tell us, the word math and discipline share the same root in Greek. It's mathetes. And Plato, in his Republic, insists that geometry will draw the soul towards truth and create the spirit of philosophy. And so as we learn about the order of mathematics, our hearts and our minds become attuned to the order in the world. And we learn to seek and love that order in our daily lives. In short, a mathematics education prepares the mind for the love of wisdom and the soul for the labor necessary in securing it. And so to scale that into maybe 3 words, why do we study math? Because math is filled with order, because math is filled with beauty, and because math instills in us a sense of wonder. We live in a cosmos. That's one of the foundational things that we believe here in a classical school, is that there's order out there, and that we can, as rational thinking beings, we can detect and determine what that order is. And math gives us a way to see that order and make those predictions. And because of the way that human beings are wired, when we see that order, it's pleasing, right? I could go onto YouTube right now and look up like the most satisfying video in the world. And it's just these videos of people that place things into the right order, right? It's people like turning a clock so that it fits just right. And these videos have millions and millions of views. And it's just people setting things in order because there's a beauty to it. We're drawn to it. And that's what math gives us. And sometimes that order pops up when we don't expect it. And that's where the wonder of it comes in. Sometimes we expect to see chaos, or we expect to see randomness when there's actually an underlying pattern. One of our juniors wrote this for a paper for me this year when they had to talk about the order, beauty, and wonder of math. This is what one of our junior girls wrote. There's a structure within chaos, pattern within randomness, method within madness. This becomes astonishingly clear when one approaches mathematics and must look closely at the formulas, postulates, and theorems that govern our seemingly untamable world. While this numerical analysis is a process initially dictated by logic and reason, one cannot help but experience a sense of awe and wonder when these patterns emerge. And this is when human emotion comes into play. With the discovery of order within chaos, nature not only begins to make sense, but also becomes truly beautiful. There's a profound beauty in the natural world's simultaneous unpredictability and pattern. And the desire to understand that thus demands both a logical and emotional effort. The study of mathematics highlights this innate duality and calls us to both understand and admire the ordered beauty of the natural world. This is one of our students that recognizes that just like the study of a really good book doesn't just necessitate that you understand the plot, doesn't just necessitate that you can understand logically how to break down a poem, but that it requires an emotional investment. You have to learn to love the characters, or perhaps you need to learn to hate the characters because they are doing something that is inhuman. There is a sense in which we need to love the math that we study, and that's what we're going for. We're going for loving the order and the sense of, wow, how did that happen? Now, that's a pretty high billing, and I might have some of you at this point going, that sounds all fine and dandy, but how are you actually doing this? So what I'd like to spend the next few minutes talking about is how at ACA and in a classical liberal arts education are we really doing this? So first, how does our content emphasize virtue? Well, one really great example, as Mr. Knowles was saying, is our Singapore curriculum. Singapore encourages our students to not simply learn what a couple steps are and move on from there. It encourages students to wrestle with an idea, to really appreciate it from various angles. Just like in life, when you have a problem, you don't want to simply look at it from one angle. You need to be able to put yourself in the shoes of many different people, approach it from, what if I saw it in this way? What if I saw it in that way? We encourage students to do that with a math problem. What if I saw division as passing things out to 5 different people? What if instead of seeing division as passing things out, what if I saw it as filling things into a different bucket? How much can I fill each bucket? And there are different ways that we can see division. There are different ways we can see a lot of different problems. Another way that we really encourage that is many of our classes, in particular our geometry classes, are very proof-based. And proofs require courage. I can tell you without a doubt that the most common reason a student will get a poor geometry grade is that it's left blank. And that's because it is very scary to know that this is where your proof starts. This is where your proof must end. That first step is a terrifying step. Because if you get it wrong, you're going to head off in the wrong direction and you may never make your way back. You may have to retrace all the way back to the beginning. And it's scary to think that that might happen. And so it takes a lot of courage to be able to take that step and say, I'm going to step here. And from here, I'm going to take the next step. And it requires a lot of creativity too. We talk a lot in math about how after you learn to add, you learn to subtract. So you can go back and forth. After you learn to multiply, you learn to divide. So you can go back and forth. So when you approach a proof and you know this is where I start and this is where I end, you think this seems like a good first step. And if I'm going to end here, I should probably be here right before that. And students begin to see how you can piece together a problem until you meet in the middle. And that emboldens our students to really do that. Another way that our content can emphasize virtue is one that I think we're really going to be pushing for here in the coming years. And that's introducing things like number theory and graph theory and these parts of math that fall into the general umbrella that's known as recreational math. Think of it as things like this. If I make this shape, I picked up my marker to make that shape. Could I have retraced it in a way that I didn't have to pick up my marker? Can I make a box with an X in it without picking up my marker, or do I have to? Or to count how many triangles are in this shape. the beauty of these is that anyone can do this, right? We can, as long as you can count, as long as you can draw, which starts at our littlest of littles, they can start to ask questions like this. And yet all of you as adults are probably looking at this and it's taking you a little bit of time. And you're probably trying to find patterns like, well, I don't need to count 1, 2, 3, 4. I know there are 4 of this shape. And I know that there are 4 of this shape. And so you can create these shortcuts. And after all, that's a lot of what math is creating these shortcuts. And so playing around with math is another way that our content can emphasize the virtues. It can emphasize that curiosity, that wonder of math. Like Mr. Andrew was saying with our 3 3 legs of the stool, 3 points of the triangle, we have really excellent teachers. I love being a part of the math department here. It's really exciting to work with my colleagues about what they do and what they're passionate about. And so I want to talk now about how our pedagogy, how the way we teach, not only what we teach, but how we teach can help emphasize virtue. And so Mrs. Wilson has sort of introduced and pioneered in the math department this year that we're going to be talking about the 5 common topics. This is pulled from Aristotle and it asks questions like, how is this problem similar to ones I've faced in the past? How is it different than ones I've faced in the past? How can I connect this problem with ones that I know how to solve? What's the authority behind this? So what are the laws that govern this? So for instance, if I'm teaching distributing, I'm a teacher, see, I have to have a whiteboard behind me. I tried as long as I could to make my points without it, but now you all get a little math lesson. So we might introduce something like distributing like this. How is x parentheses 3 times 12, 3 plus 12, different than 3x plus 12? Thank you for spotlighting me. Well, a student might be able to say the x and the 3, they're switched around. And then we would ask them, well, why does that matter? And they could come up with the rule that governs this problem, which is the order of operations. Please excuse my dear Aunt Sally. And we could say, now what's the problem with the order of operations here? Well, it's that in the first one, I can add 3 and 12. I'm allowed to do that. But when I'm asked to add x plus 12 first, I'm not allowed to do that. I'm not allowed to take an x and add it to a 12 and get some new number. And so this highlights the second thing that we strive to do in the math class, and that is ask a lot of questions. We ask our students not to simply sit there, write down the steps that we give them. We want to ask them the same questions that the brightest mathematicians in history asked on their way to discovery. We don't expect that they can, out of the blue, create algebra. That's a tough undertaking. But we believe that with the right guided questions, that they can feel like they are discovering it, that they can discover some of the truths that were there all along. And so we ask them, if I'm not allowed to do parentheses first, what operation does the order of operations say I should try next? And I don't see exponents, so I should try multiplying. And we find out that multiplying is exactly what distributing does. And so we can move from this, what do I know? How is this different? Into a mathematical discovery of this really powerful tool called distribution. And it's a blast to get to see students do this. And then, because again, we don't expect that our students are all going to create math, thousands of years of math on their own in their short 12, 13 years here. We take the time at the end of class to give a summary of our discovery. We take the time to say, now, I am the teacher, I am the authority. And I'm going to help us tie these vague notions we have together and say, there's a rule out there that says A times B plus C is AB plus AC. And this is a rule and you can trust it. And so we have these students learning to be self-governing in their education. We have these students who are learning to be courageous. It certainly takes a lot of perseverance, as any of you who have helped your students work through their math homework. It certainly helps students become just more able to tackle difficult things one step at a time. I want to end here until you guys maybe have some questions with the idea of, now, how does our kindergarten connect with our 12th grade? How in the world do we keep a common thread of math? I keep alluding and we keep hearing everyone say that math builds on itself, but what does a calculus class really have to do with first graders? And so what I want to do is first turn on my light. I apologize. You get to see what my students see every day. And that's that I must not move around enough when I talk, because my light always turns off on me. So I want us to talk about addition for the next couple minutes. Now, any of you with the little ones or who have had little ones, you know that when you start to add, you're counting very definite objects. You look at your hands and you say, how many fingers do I have? And you can count them out. 1, 2, 3, 4, 5 on this hand. And when we learn to add, it's simply counting. If I want to do 5 plus 2, I simply count how many fingers are up right now. And that's how adding begins. In a few years, once students are used to that, they have to add different sorts of things. Soon they might have to add fractions. They might have to cut up an apple or cut up a pizza and say, if I eat 1/4 of a pizza and my brother eats another 1/4 of a pizza, how much of the pizza have I eaten? And now we're not simply adding 1 plus 1, we're adding this thing called a quarter. We're adding something that's a little bit different, so that 1/4 plus 1/4 equals 1/2. Somehow we made 1 plus 1 equal 1 in a certain sense. And that takes a few years to overcome the novelty of it. That's a difficult thing to do. And then we have to figure out, how do I add 1/2 and 1/3? I have to change 1/2 into something else. I have to change 1/3 into something else. I have to change them into 3/6 and 2/6, and somehow put those things that are now common together. And it's great how that we have to turn them into something common leads us into algebra when we're adding things like x's and y's. And we have to say, now, if I can add a 1/4 and another 1/4, what would it look like to add an x with another x? Am I allowed to add something like x to something like xy? And one of my favorites is to say, well, are grapes the same as grapefruits? Or are pineapples the same as apples? Well, certainly they're not. So just because we see an x in it doesn't mean it's a like term. We need to be very specific. And so we're still learning how to add, even in the junior high or the high school, when we're learning to add things with variables. And pretty soon it's not just a single variable like x's plus x's. We're adding entire polynomials. We're adding x cubes and square roots of x. And we're adding entire polynomials. And you would think that it would end there. Finally, in Algebra 2, we've reached the end of adding, but we're not done yet, because in Algebra 2, we graph a lot of things. And do I have screen sharing abilities here? Or I think I'm getting my screen sharing abilities. We can add graphs. I hope the suspense is just killing you right now.
You got it. Abilities are yours.
All right. So we can add graphs. This is something that we talk about in our pre-calculus classes. You all can see here these straight green lines. And now you all can see this nice wave, this purple wave, that's called a sine curve. And it's one of our favorite things to look at in pre-calculus. And believe it or not, if I add enough things that look like this purple curve, I can get those straight green lines. Because if I take this purple curve and over here, look, I just add some 2's to it somewhere, and that kind of gives me a baby curve, right? Now I've got a baby blue curve. And over here, you can see that this is what happens when I add the purple to the blue. I get this new purple curve. And you can see that it's a little bit closer. It goes down when it's supposed to go down for a little bit longer. And it goes up a little bit sharper. So what happens if instead of adding 2 of them, I add 3? Well, now I get this orange one and it's a little bit closer. What happens if I add 4 of them? I get this black one, it gets a little bit closer. Now watch this, I set this up so that now instead of adding 4 or 5, we can watch this number grow into the hundreds of how many I add together. And this is what my graph starts to look like. All of these waves slowly add up together to become this straight line. And it seems like magic that this happens. And in fact, this is something called the Fourier series, where I could draw any line that you gave me, I can draw it by adding up those nice little waves together. That's amazing. That's incredible. And our last one, because we can't leave calculus out of this because calculus is so fun, we add even in calculus classes. That's right, the dreaded thing that all college engineering majors have to take, it adds. And what it does is it says, well, I'm tired of adding and knowing where there's an end. What if I add things to infinity? What if I don't just add a half and a quarter? What if I add an 1/8 to that, and a 16th to that, and a 32nd to that, and a 64th to that? And what if I keep going for forever? Well, we've got a nice picture for it. This is one box. This is half of a box. This is 1/4 of a box. This is 1/8 of a box and 1/16. And I could keep writing what parts of a box this is for infinity. I can keep cutting it up into smaller and smaller bits. And I find out that if I add up into infinity, I can get the number 1. By adding for forever, I can get the number 1. And remember, adding started with this idea of how many fingers am I holding up? And that's the journey that students can take in math from the first grade through their calculus or pre-calculus classes. It's a blast to be able to do it. And thank you so much for listening in. Mr. Knowles, Mr. Andrew, if you have anything to add, or parents, if you have questions, we would love to hear them.
Yeah, certainly would encourage, again, if questions come to mind, that parents can put them in the chat. And one of the encouragements I would have is really just as we think through what math is at ACA, that we would consider the 2 things that Mr. Clausen just pointed out so well, is that on the one hand, we're dealing with content and skills, and so much in the practical development of mathematical skills and even instincts, but also, as with each subject that we teach, that we are seriously considering the weight of how they're shaped as human beings by what it is they're doing. It is not lost on us that sounds grandiose to be thinking. I, for instance, have a 2nd grader, to be thinking about, like, how is my 2nd grader shaped as a human being by math, right? But there is a sometimes subtle sometimes not so subtle way in which that happens. So Mr. Clausen, thank you so much for walking us through that, even considering ways in which we are pursuing virtue by our pursuit of mathematics, and thinking through ways in which we can play and see things even as a bit magical, in the process of how we're considering math. I would leave as we're thinking through, if there are any questions that will come through, we've made space for them, just with an encouragement for parents, knowing that we have a range of parents who are on the call this morning, whether you have a high schooler, or a student who's in elementary school, of find ways to play with math a little bit, to ask questions, to normalize even discussions around math. A lot of times, one of the biggest hindrances to mathematical growth in a student is math, I think, uniquely among other subjects, lends itself towards students pigeonholing themselves very, very early. Which is to say, even in lower elementary, you will find there being times when students will say, "Oh, I'm just not good at math." Very quickly that can happen. And so one of the things that I think Mr. Clausen did such a good job pointing out is that math is not just about sort of performance. Yes, math is unique, and sometimes the student's brain wiring might lend itself toward math in a particular way. But you'll never hear us say as faculty members like, "Oh, you're just not good. I'm just not good at math," whatever the thing might be. We are believers that every single student can grow in their mathematical abilities, and every student can grow in their ability as students. And so find ways as parents even, to play around with numbers a little bit, to consider how is it, that we would be in a position where we can think through, math being a part of normal life. My second grader, Mari, has found it to be fun to try to find ways to challenge me in math, which is incidentally not that difficult. And so what she will do is she'll be like, 8 + 8, Dada, what is that? I'm like, well, you can do that. You got to tell me what that is. Okay, it's 16. All right. What's 16 + 16? I think you can do that too. And we'll do like play around with it a little bit. And then she'll just keep going from there. What's 32 + 32? What's 64 + 64? And she'll go again and again and again and again. So we get into the thousands, and I start having to really stop and think, and most of the time mess up sooner rather than later. And a part of what the fun in that is not only does it become a game of sorts, but it normalizes even just kind of standard conversations around math and around what it is. So to get them thinking about, okay, addition, 32 + 32, that's 32 times 2. As they get older, that you can connect this to even more practical, things in life, whereas they're thinking about work and money and taxes and percentages and all those kind of things. There are ways to make this a more even kind of normal part of life and conversation. Obviously, that has to look different depending on the age of students, but we really want to emphasize that sense of, math has the potential to shape who we are, and we want to normalize conversations, around mathematics in particular, and really seeing that, we don't want students to pigeonhole themselves early, but every student has the capacity, to be meaningfully involved in the learning of math. That said, I would pass it along to Mr. Andrew, and we'll see if we have any other questions that show up.
Oh, a question from Dr. Roth, and I think that perhaps there's a classical root to this question. If Achilles were to race against a tortoise and Achilles covers half of the remaining distance every second, who wins? I think this is a question about limits. I think we might eventually get to adding up to 1. I would let Mr. Clausen take a stab at it. I do want to offer one brief comment here. As Mr. Clausen was describing teaching math classically, I think the thing that my mind immediately goes to is the way in which this approach facilitates a new encounter with reality for our students, that students might actually see the world differently if they know to use their mathematical instinct toward trying to discern order in the world. Right? They might actually see the natural world, the things that they interact with every single day, differently. They might acquire a new vocabulary for describing the world. I remember going to Washington, D.C. with our students for the first time and walking into the Capitol building with them, and there were a bunch of school groups, and they were all kind of remarking on what they were seeing, and there were a few kids that were just saying, this place is huge, this place is crazy, this is where laws get made, or, you know, why is this building so round, why is it so tall, why is it, you know, we're all kind of straining to find the right words to describe the grandeur of what we're beholding. And one of our students very eloquently began to describe the rotunda and describe the Corinthian columns. And what was apparent to me was that his capacity to appreciate the grandeur of a place was connected to him finding a formal vocabulary for it. He was able to have a more precise appreciation for the world, for an incredible construction of man, because he had a language for it. And what Mr. Clausen is suggesting is that if we can provide our students the language of mathematics, the vocabulary of mathematics, they will see something different in the world. They will perceive order where others will perceive chaos. And it's easy to understand how an education in English might do this, right? How an education in English might order a person's virtues and dispose them toward pursuing truth and understanding what is true, toward pursuing what is good and understanding what is good, toward perceiving what is beautiful and looking to create beauty themselves. But mathematics offers this same opportunity, and it's remarkable to have just these little examples that give you a window into it. As Mr. Clausen was offering that example of those signs eventually, you know, becoming a line, I chatted to Mr. Knowles, this is magic, this is fake, none of this exists. It's impossible to wrap your head around sometimes, but you know, your soul, something in you kind of yearns to understand it, right? And your students are experiencing that same thing. I think this is why math is hard for our youngest students sometimes, because they say, what is a one? What do you mean that 1 and 1 are 2? And because we sometimes struggle to explain to them what 1 really means, we lose them and they begin to think, well, I must not understand math because I can't really understand what this one thing is. In fact, they're inclined to ask a deeply philosophical question about number theory. What is a 1 and what is a 2 anyway? And our struggle as adults to kind of make that connection and perceive that intuition is a limiting factor in their education. But when we have teachers like Mr. Clausen who can open up the world to those students, engage them in a conversation about number theory, about the way in which mathematics offers you a new vision of reality altogether, the ceiling is impossibly high. There is so much room for growth. And so this presentation was thrilling for me. I took lots of notes. It's also recorded, so I'll be going back to it and would encourage all of you to do the same. I don't see any questions. You all know Mr. Clausen's email, so feel free to reach out to him if you have any or just want to follow up for a math conversation. I'm sure he'd be happy to engage in one with you. So again, thanks so much for joining us. We'll end things here, but we'll see you sometime soon. All right, thanks everybody.
Thanks for being here.